Thank you for this opportunity to be able to give this lecture here. A lot of people from a lot of disciplines have contributed to the results, and you can see some of their names. Let me just point some principal components of this. There's Gabriel Curio, who is a neurologist by training. He's with the Charité Berlin, which is the biggest medical school in Europe. And Benjamin Blankertz, who's over there next to Lieven. Benjamin is a mathematician by training. I'm a physicist by training. So all of us are assembled in the Bernstein Center for Neurotechnology, which is a very nice center that the German government has been generously funding. So I think that is as well. So let's start. I will use this public lecture for teaching you some of the background how to build a brain-computer interface. And it will be very basic. So for those of you who expect lots of equations, I only have few equations, okay? But I have some, because also, IPAM is a math institute. So math is essential for this endeavor, okay? Okay, so let's just show you a very brief video by Andy Schwartz that is trying to show invasive brain-computer interface at its best. There's a nicer video from last December where he showed a disabled woman being implanted, feeding herself. This is extraordinary. And that is the state of the art of brain-computer interfacing. If you put these very pointy electrode arrays into a brain, so it's really like a bunch of needles, and you stick it into the brain, right? They are small needles, but you still stick it in there. And you have a brain surgery before that. You open and close the skull, right? So there's some risks to this technology, but I'm sure that there will be some patients that are very eagerly accepting this. So let me just show you. This is a monkey experiment that Andy Schwartz did. And you can see basically a robot arm here. And so what you cannot see very well is that there's no monkey arm in this, right? So for everybody who knows robotics, in this kind of robot arm, there's no space for an additional arm, okay? So what the monkey does, he's just controlling this device, this robot arm, by the power of his thoughts alone. So basically with an array of that, with a couple of hundred electrodes that are time series, sampled over time, with some intelligent machinery that we will describe later, you can decode and translate these neural signals into the control signals of this robot arm. If you look very closely, the monkey's arm is here and it's still. So the monkey has actually, through some extensive training, learned to control this robot arm. So, generally in monkey experiment, I'm not doing these monkey experiments, but generally in monkey experiments, these monkeys have to be trained for many, many months and until they understand what they're supposed to do. And then in this case, the monkey had to also learn to control this robot arm in addition to that. Okay, so I'm showing you this video because you can get a clear feeling what is possible with invasive brain-computer interfacing now. Also, I think it takes very little imagination to see where this can lead, namely neuroprosthetics. But also, this is basic research, and we have to be very careful because it's the beginning of something, and a lot of people who are disabled, they carry high hopes, but this takes a long time until this will become a clinical practice. I think this should be very clear. So what I'm talking about also in the following is really an endeavor we're in the beginning, and I think it carries great hope. But it's also a bit sobering if you see what we can do these days. Okay. Now, I showed you the invasive part first, and I will, for the rest of my talk, talk only about non-invasive work. So I'm not doing any brain surgery from now on. I have never done any brain surgery so far, just to be clear. What we do is non-invasive brain-computer interfacing. And just to be also very clear, I'm the guy who stands here and talks about it, but there's pioneers in this field. They have been working on this for more than 20 years. Bierbaumer is one of them from Tübingen. John Wolpaw, who gave a lecture this morning in our workshop, is one of them. Or Gerd Furtscheller from Austria. And they have been doing great things. About 12 years ago, this was a very small field. With these pioneers, their main motivation came from clinics, so they wanted to help patients. And for this, the patients actually had to learn to control their brain signals such that they could be decoded. This took several hours, hundreds of hours essentially, typically between 100 and 300 hours, until this status was reached. And so when I entered the field as a machine learning person, I actually asked these people, why not have the subjects think whatever they think, and let's let the machines do the learning, let's let the machines do the decoding, the statistical analysis should do the work. So there should be no extensive training. And I asked, why is it not working? And they said, well, it doesn't work, and it would be great if this works, and by the way, good luck doing it, right? And in fact, they also gave me lots of very useful advice that made us jumpstart in this. So a couple of years later, we were able to provide the first brain-computer interface where machine learning was the crux. So the learning machines would be able to, within a couple of minutes, learn whatever the subjects were thinking, and we would need about 10 to 20 minutes of data from the subject side. So this was a huge difference between 10 or 20 minutes of calibration, 200 or 300 hours. So this made the whole thing very practical all of a sudden. And then there was an explosion in the number of groups that started this field, and also non-clinical groups became interesting of the possibility of being able to decode thoughts in some sense, in some broad sense, okay? So let me just be a bit more precise. So in the case of brain-computer interface, you need ingredients, which is what a brain. You need some measurement device. So for example, in our case, because we're doing this non-invasively, we have EEG, electroencephalography. So we get sample some signals. Then, because I'm a machine learning professor, I guess we have to do some feature extraction and some classification, and with this we get a signal out, and with this signal we may control a wheelchair, a computer game, we may communicate, we do all sorts of things. So once we have a bit out of the brain, metaphorically speaking, then we're in the business of brain-computer interfacing. So the whole point, of course, is, so in the strict definition, the brain-computer interface is a device that translates human intentions, but without using peripheral nerve activity and also muscle signals. So, in other words, if I start wiggling my ears or doing all sorts of games, then this is an EMG, electromyography, muscle-computer interface, not a brain-computer interface. So if you look at some of the companies that sell now brain-computer interface games, they rather sell you some EMG computer interface games, which may still be fun. But so we'll be, strictly speaking, only looking at brain signals and at this BCI type. And what I will, my main focus, because we brought this machine, let the machines learn idea into the game, is the decoding part. How can we decode these brain signals? And I will just go through this whole process with you, and then we'll see what we can do with it. Okay? So first of all, the classic thing is that you would like to use a BCI for communication. So you would like to have a patient, for example, write a letter or communicate with his environment in some way. Okay? So let me just, as a contrast to the monkey video, show a human video, right? And for some reason, I happen to be the subject. And it's about 2003. This is the NIPS 2003 poster that is on the wall. So you see a standard EEG. In this case, we typically use 64 channels, but we could do with less. So then there's some wires going into a box, which is an amplifier, and then it goes into a computer, and the computer translates these signals that we sample with the EEG. So just to be very clear, an EEG measures cortical activities only, and it measures about 10 to 50 microvolts if we can be happy with this signal. So it's very small signals, and you need about at least 10,000 neurons that are simultaneously discharging in the same manner in order to be macroscopically measuring that. Now, if I do this, right, there's hundreds of thousands of neurons that are active, so you would be clearly able to see that with EEG non-invasively. Okay, but I should show you the video. So what I will be doing is I will be controlling this cursor down here with my thoughts alone and trying to play the game of Pong. And so there's this blue ball flying, and I would try to put the cursor below it so that I can play. Right. Okay, so there you go. So, of course, in this case, you can ask me, how is he doing that, right? What did I imagine? Because you don't see my hands twitching, or I'm fixating the wall over there, so I don't control this with my eyes. I'm not chewing or wiggling my ears as far as this video shows. So what am I doing? Well, I'm actually imagining movements. Okay, so I'm in this case, I'm imagining pulling a virtual string. So, which means that I use my virtual hand and pull a bit to the right or to the left, right? And this is translated into a control signal in this case. So I have two brain states, left and right imagination, and I can distinguish between them, and we'll see how and what kind of neurophysiological signatures are coming with these signals. Now, it's clear, I mean, it's probably not only German professors should be able to do some string pulling, some virtual. Anyway, I mean, so I think it's a very natural thing to imagine something that has to do with the game, left and right, okay? So, what are we doing? So, and what are the challenges? So first of all, if you measure this EEG signal with 64 channels, there's not only me imagining some string pulling action, but I'm also looking at above the screen, I'm listening, I'm doing all sorts of things, and my brain is active in all sorts of areas. So basically all these areas are active at the same time. And since this is an electrical signal that we're measuring, all these, the signals of all these areas superimposed by Maxwell's equations. So the only thing that we can measure with the EEG is a superposition. So what we would like to do is we would like to concentrate on one source that is, for example, linked to the string pulling, okay, which would be maybe near the motor areas, okay? And all the rest we would like to treat as noise. So I call this the cerebral cocktail party problem because it's very similar to the usual cocktail party problem that we will face later on in IPAM. So with a lot of people talking at the same time, but still with our binaural hearing, we are able to home on the person that we are talking to. In this case, we take a statistical beamformer and just concentrate on some brain area and discard the rest. So there's a lot of math to this, but I don't talk about it. Instead, I will talk about the physiology. So when we imagine, so first of all, we know that the brain is generating all sorts of rhythms. And I think the most popular rhythm, and in particular, if you would put an electrode on my brain now at 2 a.m. Berlin time, okay? So there would be high alpha activity, okay? So if you would close your eyes, then, and I put an electrode here occipitally, then there would be an idle rhythm at about 10 hertz that is called this alpha rhythm. If you open your eyes again, then this rhythm would be suppressed. So same here, if I just wave at you as I did before with my left hand, then on the right hemisphere, there's an idle rhythm that is suppressed if this arm moves. If it's at rest, this idle rhythm is kicking in. So there's a suppression of a rhythm. And the interesting thing is that this rhythm is also suppressed if we imagine, say, left hand, not move the left hand, but just imagine pulling this string, then also a rhythm on the right motor cortex is suppressed. Same if we are imagining now right movements, then on the left motor cortex the rhythm is suppressed. So that's very useful because if I do the string pulling, I would look for signals whose variance is suppressed, lateralized, in a lateralized way, as they say. So that's our signature that we're looking for. So there's another issue. So there's the cocktail party problem. We know what the physiology is about these suppressions, and then we should take a look at the signal. And now we take a look at the signal at one electrode, okay? And so we do some imagination of the left hand and some imagination of foot, right? And you can see the blue curves are foot and the red curves are left imagination. The solid lines are averages over many of these imaginations, and you can distinguish between them. In the not so solid curves, they are single trials. So you imagine left, and you do it again, and you do it again, and this has considerable variance, as you see. So in the case of a brain-computer interface, you cannot do what usually is done in neuroscience, which is you average over many trials. But you have to do the decoding on a single trial basis. So otherwise it would be terribly slow. So, but of course we know that the brain is a real-time machine. So the difference between single trial and averaging is very nicely put into in anecdotally by thinking that you walk through the jungle and then there's a tiger jumping from behind a bush at you, okay? And so it's clear that you can make the right decision, namely to run or to jump the other way. And you don't need to tell the tiger to go back behind the bush and do it 1,000 times so that they can average and make that decision. So we are on single trial basis, okay? So it's a mess in one single channel, and it's a mess in 64 channels. Now let's look at another source of variance. So let's look at one subject at one day doing this left-right imagination. And you can see the maps. The black dots are where the electrodes are sitting. The triangle is where the nose is. It's a picture from above of the brain and of the voltage distribution. And you can see that there's a little knob here for left imagination on the right hemisphere and for right imagination on the left hemisphere. So that's on average. So on another day, it looks like this, and then some week later and some month later, okay, so it looks a bit different from day to day. And of course, this is well in line with our experience about our brains. We're not always in the same state in the morning. Okay, so we have to deal with that. And then, if you think about different subjects, last slide was one subject. So this is one textbook subject, so to say, imagining left versus right. And these are just a whole bunch of different subjects, 30 of them. And you can see it looks all quite different. And and they are neurophysiologically perfectly normal as far as we know. So it's a big variance, and I think, of course, the technique that we should apply is machine learning to deal with that. Okay. So then let's put you through the protocol. So first of all, if you would come to our lab in Berlin, the first thing is you get this cap on. It takes some time because we put gel into these electrodes, and later on you need to wash your hair because it's a mess. Okay, so then you have this protocol of 10 minutes training where you would generate the data for the machine learning method. And then we have the data, we put it through our inference procedures, and then we go to an online feedback session. So the whole thing can be done easily within, let's say an hour or so. Okay? And of course, the idea is let the machines learn. So it's not the subjects that learn because they just provide 10 minutes of data. So now you should be doing this because, then you get a better impression how hard it is actually to collect this data. It is harder for two reasons. First of all, EEG is prone to a lot of artifacts. So if you're sitting there and chew or talk or whatever, this creates huge signals, so everything else is very small. So you have to be relaxed. On the same token, you have to be very focused to generate these brain states. Okay, so let's try that. Entspannen means relax. Okay, so you relax, and you will see something on the screen, a letter. And while this letter is there, you will relax and focus, imagining, say, a squeezing of your ball with your left hand, or kicking a penalty for your foot, or hitting with a bat with your right hand, something like that. And of course, they have different skills. Okay, so start. So now left imagination. Not anymore. Left again. Not anymore. Left. I can take a drink. Right for a change. So this is going on for about 10 minutes, 20 minutes. And so it's very boring. When I was a subject and I had my son was born, I would immediately sleep after 5 minutes, which gave a great motivation to actually make algorithms that can deal with very little data. Okay, so what we have now seen is that all of you have generated two different brain states, left and right, imaginations. And then, so we've gathered some EEG data, and the idea is now to infer some spatial temporal filter that is individual to you and that allows to solve the cocktail party problem, just focus on what is necessary for the communication purpose, and then we put this through a classifier. So just to be a bit more precise, so what we have are these two kinds of signals that you just generated, where you suppress the variance of your right and suppress the variance for the left, and then there's all the other non-specific issues of variance, artifacts, whatever. They are all projected into what we measure. That's the EEG. And now we are here, we should build some kind of filter such that we can distinguish between the right and the left things and just discard all the rest. So that's the idea, that's the program. And now is some math. So this is like the simplest possible way of addressing this. So now imagine you're not in the 64-dimensional world because we are measuring with 64 channels, but let's consider just 2 channels, okay? And now channel 1 and channel 2, so to say. And then we have some trials, the left trials and the right trials, the green and red dots. And now we would like to find a method that can help to distinguish between them, okay? And basically we are looking at the variance of this data set, and we take the sum covariance matrix, that's the blue cross. And the first thing that we do with that is we sphere it, we put it onto a ball, okay? So this means that we try to find a projection operator P that tries to put this into a ball, okay? Then we redefine the covariance matrices. So then the next step we do is we have this data that is now on the ball. So the only degree of freedom that we still have is rotating this ball, okay? So why don't we rotate it in this way, that one direction is very good for decoding one class, because if we decode in this direction, then we get the green class and the red one shrinks to a point. If we project to this direction, then we get the red class and the green one shrinks to a point. So that's called a common spatial pattern, and it's basically computed by a whitening operation and then the additional diagonalization and 1 minus diagonalization. So that's very simple, just linear algebra. If you didn't get it, then we just have a video. So this here, what you will see in the video, is basically the voltage distribution over the brain, and the axis here, the crosses here are basically single channels. So I picked out 5 single channels just to show you what a mess an EEG signal is. Okay, and now we have inferred the filters of right imagery, which is a knob sitting on the left motor cortex, and left imagery, which is a knob sitting on the right motor cortex. And then we can just look at things. So this would be a filter ideally allowing us to discriminate between these two states, left and right. Okay, so let's look at this. Okay, so now the subject is imagining white. So because the subject was instructed to do so. So if you look at the EEG, so if you look at this, you don't see anything. If you look at this, so right imagery means that there should be a suppression of a rhythm on the left hemisphere. If you look at this, it's not really there. You cannot see it. by eyeballing, it's hard. So, but then we apply our filters that we just estimated with our linear algebra procedure, and we see that this filter has a very nice signal that is suppressed, whereas this one has a higher variance, okay? So we can distinguish between a right imagery, because this one has a small signal, and left imagery, because this one has a large signal, okay? So let's continue. Okay, so now the subject is imaging left. So now this guy is getting the small variance signal, and this guy is getting the large variance signal. And in principle, you should be able to see that, but you don't, because it's an EEG. There's lots of things going on, right? Okay, so that's basically what we do. You can play this game for a while, but I stop this. And if we plot the log variances in this particular game, then we can see that it's very nicely distinguishing between left and right imaginations. So if we look at this more closely, we have to do a bit more work. So because this was a bit too easy, it's not very robust. So in fact, what we have to do is we have to do some artifact removal. And so what I showed here is these spatial temporal filters. And we can also use all sorts of other physiological signatures. What we do is we filter this data, the EEG data, with these filters that we have inferred with our linear algebra procedure, stack them into a vector, and then build a classifier to distinguish between these two brain states. And this classifier may be some mathematical program. For example, like that. It may be one of my favorites would be a support vector machine for obvious reason, but it could be some LDA, whatever you wish. Okay, this is now the mathematical program written is Fisher. And since Stan has been asking me, where's the sparsity, right? There's your slide. Okay, so we can now ask a question. Okay, so we have machine learning, which is a very nice tool. And we have some neuroscience experiment. Can actually machine learning tell us something about the physiology? And in this case, we already know the physiology because it's clear. It's left and right imagination. But we can just behave as if we wouldn't know, okay? So let's think about the following matrix, okay? So here's, with our data, we have now the following matrix. So we have all the channels. So we have the frequencies, and we have the trial structure. So it's actually a tensor, right? But we are looking at channels and frequency for a minute and just collapse all the trial structure and average, okay? So then we get this kind of, so we have, just to remind you, the left trials and the right trials. So we can put this kind of tensor through our classifier, okay? And since, I promised something sparse, we can put it through this wonderful sparse linear program written down here. And then we can look, so what does the program tell us about what is important in this tensor, okay? And that's what this matrix is about. So here's frequency, okay? So if we average everything along all channels, then we get that the salient signal is somewhere between 10 and 13 hertz, which is the alpha rhythm, or the mu rhythm in the case of motor imagery. So if we are actually averaging along this direction, we see which channels are important. And we look at the channel distribution, okay? And we see that there's a nice little hot spot near the motor cortex. This is like foot imagery. So you can see that this averaging, you can see this little plot. So by just taking any old cognitive states that we can think of, doing the experiment, then running this through a classifier, we can infer what kind of frequency and what kind of spatial distribution we expect. So for the case of motor imagery, this is really trivial. We are just reproducing existing physiology. But there may be some other more interesting cognitive states that we may have in mind where we don't really have a clear model of what we would expect. So then we can already get some idea of which areas in the cortex should be contributing and what frequencies. And then we can try to adapt our experimental paradigm to actually test this hypothesis. Okay, so in this way we can hope to learn something. Okay, enough for your slide. Okay, so now we are going to feedback. So we've done all this 10 minutes of training. We've done our machine learning, solved our linear programs or mathematical programs, and then basically, so in the calibration session, we have built our feature extraction chain, we have a classifier, and basically the only thing that remains is taking, if you think this is the continuous signal, we take a window, slide it over our data, extract in this window the features, and run it through our classifier, and done. And this can be done in a normal cell phone. I mean, nowadays these are supercomputers, but I mean, anyway, so it's not taking a lot of computing time. And so then we can start communicating. So here's one, because we have one bit out, right? Left versus right. So, and this is now the hexospell device, because it's made of hexagons. And I think it's clear for you already now that this is a multidisciplinary endeavor. So it's math and physics and computer science, neurology, neuroscience, lots of things. So, but yeah, I mean, you have to wait a little bit. You have to be a bit patient with this video. Anyway, so the whole classification of an EEG signal is something intrinsically probabilistic. So the question is, how to design an interface that takes into this probabilistic nature into account? And we came up with this hexospell device where you have one brain state that turns the error and one brain state that extends the error. And you have some slack in the extension and in the turning, so that can take this probabilistic nature into account. So we went to the colleagues from Human-Machine Interaction, Roderick Murray-Smith, also a partner in the TOBI project, and this was like the outcome of it, right? And so with two choices, we can basically go to any letter in the alphabet, okay? And you can see that it's less vicious than you may have thought. So the sentence would be "Die Sonne ist von Kupfer," which is one of the first sentences transmitted by the telephone, through the telephone by Reis. So just to say something about this video, this was taken at CeBIT. So CeBIT is the largest computer fair that is on at the moment. It was opened by Angela Merkel, I think today or so. And so it's not a video of this CeBIT, but CeBIT 2006. And so you can imagine that this subject was actually, sitting in front of the screen, trying to imagine his things, relaxing and focusing. And there would be about 40 people standing around him, 2 camera teams. And, now you relax, right? There was another thing, which was that behind this white wall, there was a main power supply of Hall 8, a cable of this size. Imagine EEG is doing 10 to 50 microvolts. Okay, so this basically shows that it's quite a robust thing. And so Guido, Guido Dornhege was the subject. He was really, keeping his patience with all what there was and not misspelling except once when the German science minister came up to him and put her hand on his shoulder. get the picture check. Anyway, so this was quite stable. Okay, so just to show you, if we are looking at the distributions in this brain, now I cannot show 64-dimensional plots, right, of left and right class distributions, but I can show projections down to 2 dimensions that are coarse approximations. Then what is happening actually within one of the experiment, not the one in CBIT, but another one, is that the distributions change quite a lot. So from the machine learning point of view, this is good news because it's work for us. From the general point of view, it's really bad because in machine learning, we just assume that everything is stationary. So, but by the way, everybody in machine learning and statistics assumes stationarity. So this was also one point where we understood that we have to do something about it. We have to do some research about it. But I think that's another story. Then, okay, I think I think it's a good idea to stationarize this distribution. And in the morning, I talked a bit about this. So I just skip over these things. So let me just show you one thing. If you are able to stationarize well, then you can also do, what is maybe the fastest non-invasive communication with motor imagery. So just to show you. So this was our subject. And we have this pinball machine in Berlin. We did some serious soldering. And so we have left and right imagination. And we're now able to control the pedals of this pinball machine. And this is quite stressful for the subject because this is real time and you're really immersed in this. And it's also probabilistic because you have no clue where this comes from. And it's a reaction time thing. And also it's a timing and dynamics thing, as you see. And it doesn't work always well. And it's also very subject dependent whether you can play this game. I can't. I can play Pong very well, but not pinball machine. We had a journalist come in the morning. He never played this before. He never did BCI before, but it turned out that he spent part of his studies studying also pinball machines. So he was quite a pro in this, but it also transferred to being a pro with BCI. Okay, so just, so this is very playful. It's very good because you get lots of student volunteers to participate in the experiments. But on the other side, it's a very serious neuroscience question. How can the brain get the timing and the dynamics right under these very uncertain conditions? Let me change gears from motor imagery to monitoring with monitoring brain states. In this case, we have some kind of stimulus like this. This is a stimulus to your auditory cortex, and there's a brain reaction to this. This is called in event-related potentials. So in this case, the data looks more like a whole bunch of these time series. So there's a stimulus, and there's a response to this stimulus, and you can take averages in time windows in all the 64 channels, and you get a huge matrix, and that you stack into a vector, and then you go again through your classification. So what can we do with this? So I brought to you this one example that maybe nobody would have thought about. And the story is the following. So I have this colleague in Berlin, Thomas Wiegand, who's actually quite famous because he invented the H.264 standard. So every second bit in internet is according to a standard. He's also the only scientist I know who got 2 Emmys. So, and the question that we had was, so when people watch videos, are we actually able to quantify the distortion level of the video that is coded by H.264 and relate that to the brain reaction, okay? And so the way we formulated this was that we played some video that was undistorted or had a certain distortion level, and we changed the distortion level, and we had the people say whether or not they saw something, okay? In some cases, it's very easy. In some cases, it's hard if the distortion level is only a slight difference. And the question is, what does the brain say to that, okay? I just show you a video because then you can see it yourself. So within the video, there will be a moment when the contrast changes, and you can see whether you can see that. Everybody should be able to see that here in this one. Okay. Okay, so that. Okay, so this was easy. So your brains reacted to that. So that's the small contrast now. So you didn't see in the first place? So again, so there was a certain way of coding the video, and you can code a video that it's very edgy and very, or you can code it with a lot of bits, then it's very crisp and clear, okay? And so we played with having very edgy kind of coding with few bits and many bits, right? And so just to show you again, so this is very high contrast between a very crisp coding and a not so crisp coding. See here, it's much smoother, okay? Get it? So you can now do psychophysics. You can ask people, when do you see something and so on and so forth, and you can get these psychometric functions. For this, you don't need an EG. But you can also, play this with an EG. And there's a so-called P300 that reacts to some change. And you can see that for very strong quality differences, you get a very strong brain reaction. And at small quality differences, you don't see anything, right? So with that, you're actually able to not only have some kind of psychometric functions, but derived from your brain. You may actually also be able to see some non-conscious processing. So let's look at the maps. You can see that this is just the baseline. There's no change. Then this is a very small quality difference, a bigger one, and then this is a strong quality difference, and then this is the maximum one. So you can see this the green curve corresponds to this, and the yellow curve corresponds to this. So you can see that there's actually a quantification of this quality difference. So why can we be excited about this? So I think a lot of people spend a lot of time on MP3, designing a code so that you don't hear anything. But in video coding, all the coding was mainly done by engineers, trying to find many bits back, so to say. Okay. But the question is, can we use our brains? Can we have more brains in this video coding? And I think that's the program that we jointly pursue, Thomas and my group, and of course also Benjamin has contributed to that, Benjamin Blankertz. You've seen, just so far, you've seen that you can use BCI for communication, for spelling, for some video games, for pinball playing, and even for assessing something like video coding distortions. So it's quite amazing that you can use this channel, this new channel of being able to decode the thinking and behaving brain in real time. But let's come back to the original motivation, which was that we also would like to have some help for the patients. And so I brought to you, just in the last few minutes, some clinical study that has just finished, also within the TOBI project. TOBI project was it was a European large-scale, it's called an IP integrated project with a budget of 10 million euro or something like that. And so it brought together machine learning people like myself and BCI people like myself and clinical people and people, really in hospitals and robotics people and so on and so forth. So a lot of different, I have two hats, so to say. I couldn't resist doing that. Okay, so just to remind you, Bierbaumer was one of the first to show communication with the slow cortical potential. They had a paper in 1999 in Nature, which was like a seminal paper for the field where you could show that an ALS patient, he could establish communication. As I said, there was extensive subject training necessary. So then, now, lots of people that work in the clinics, they say, well, all this machine learning thing that you're doing is nice and good, but it doesn't translate to clinics. So, and so far, it's true, we haven't showed that, but now we're showing it. First of all, also this should be clear. Patient studies are hard and rare. You have to go to the home of a patient many times, and it's really takes a lot of energy on the patient side and on the experimenter side. And there are really too few studies where this is shown, but it's clear it takes so much energy and funding and so on. So usually for motor imagery studies, there was a very high number of sessions. And so our idea was to show that within very few sessions with the machine learning protocol, we are able to have patients communicate. So we had 4 patients. So, just to show what the diagnosis was, and just to show how many bits per minute these patients would be able to communicate with the help of their assistive technology. Because also, the issue is a brain-computer interface is very inspiring and interesting and so on and so forth. But there's assistive technology, and we have to be able to not beat it, but enhance it, right? So because the patient doesn't care whether we like BCI or not, the patient wants to communicate. Okay, so there's something that I would like to show you. So patients are seriously ill people. So, you see here the band power for one patient where you see there's a nice knob in the alpha band and the beta band. This is quite normal. This is another patient. So these are the ones that can still communicate with more than 30 bits per minute. Now this patient and this one, you don't see any knobs there, right? So there's no difference between eyes open and closed. So we have been talking about some rhythms that are suppressed and things like that. So nothing can be seen in their brains in that sense. And so the question is whether there can be something done. So here's the study design. So we had 2 sessions of preparations, then one session of EEG screening, then 4 to 8, session 4 to 8 was a BCI feedback session, and session 9 was evaluation. So overall there were about 6 EEG sessions. Okay, and so what we did was basically the same protocol that I showed. We had these so-called oscillatory features for motor imagery, but there were also slow potentials that we didn't talk about so far, but we also used them, and we built classifiers, and we had a hybrid classifier. And then the application that we have had what was Connect 4. We used it. It's a game. We used it because there's always a motivation issue for patients. So they also want to have some bit more interesting experience than the usual studies. So I think gaming was actually well received by them. So it's an easy game. It's easy to explain. It's slow and it's strategic, and we can play this with assistive technology and with BCI. You can see whether the communication speeds is different. So here's the online performance of these patients with a copy task. So you give the patient a certain word to copy, and then the patient tries to copy this with the use of the BCI. Okay? And so you can see that, in fact, the patients were quite good. These two patients that were quite good and had more than 30 bits with their assisted technologies, they didn't really have a lot of trials correct. So this one neither, but this one, he was the one who had only 0 to 2 bits per minute with his assisted technology. So obviously, he was doing very well. Okay? After only 6 sessions of EEG. So just to remind you of that. And so then here's the information transfer rates. And so you can actually see that this patient here, I mean, these patients didn't, the BCI didn't do much to them. But for this one, who was actually the one that suffered most, we could actually have a communication rate through BCI that was faster than with his assistive technology. Okay, so in that case, BCI outperformed other assistive technology. And now, this is a study with 4 patients. Okay? So it's not 100. It's unlikely that you get 100 in this field. Okay? So typically the studies are small, like this one. And there's one patient for whom you can actually show that with this machine learning approach, you could actually gain something within very few sessions. So this was, something very interesting for us to see, and it's encouraging. It's not a huge breakthrough. For us, it's a small breakthrough, right? And it gives us hope that also, we could train these patients more, and we could use more sessions, and then we can be better. But this patient was really happy. And I think this is also an important point. If you work with patients and they are able to communicate, then they're very happy. Okay. So I try to introduce brain-computer interfacing to you. We have in our Berlin brain-computer interface study, we have typically untrained people. We calibrate within less than 10 minutes. We have a data analysis that is less than 5 minutes. We get something like 5 to 8 letters per minute in a hostile environment like CBIT. We have demoed this in various contexts. Machine learning and modern data analysis is the key. There's lots of challenges. There's challenges that lie in mathematics. There's challenges that lie in interaction with patients. There's non-stationarity that we have to worry about. The workshop that we are currently doing is about multimodal data analysis, which means that what if we, instead of only using EEG, take some other measurement device as well? Maybe, can we get mileage from that? And so there's lots of challenges from the math point of view of that multimodal data. So I think the largest challenge is really patient studies, and we should do more of them. I find this very encouraging. It's the right direction. And as I said in the beginning, we are on the starting point. Will still take some time. It will not be tomorrow a clinical practice. And the press is always telling success stories. Of course, we want to read success stories, but we have to be a bit sober in this. This is a long process until we get some, standard procedure in the hospital. And it would be very nice to have that at some point. So if you're interested in reading, there's one book that is already a bit older. John Walpole's book is newer, from 2012. A lot of people have contributed. A lot of funding agencies have contributed. If you're really interested in EEG and you don't own one yourself, there's data on the web. There's a series of competitions that we have been doing over the years, where we had high quality data, put it online, and this was actually one of the starting points where neuroscience data was made public. I think the BCI competition was I think maybe one of the first even. So there's lots of information that you can get if you look at the BBCI homepage. And I think not only data should be public, but also software. Yeah. So thank you very much for your attention.